Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. In the last class we derived the mass conservation equation using the Reynolds transport theorem, and we said that depending on what extensive quantity that you are going to use, you can basically derive the mass conservation, momentum conservation or the energy conservation equation. So, today we are going to derive the momentum conservation equation. Okay, so if you use B equal to basically mv, okay, you can get B will be V, and you can derive, you can get this expression which will be similar to the mass conservation, but will have more forces or more stress terms in your momentum conservation, right. So, that will give you rho u I by dt. Why I here? Okay, because momentum is a vector quantity. So, you can derive it for individual velocities, okay, individual directions I, j and k, right. Mass and energy are scalar quantities, okay. So, you will have just one equation, right. So, this will be del by del x j rho u I u j, and then this is basically your basically rate of change, okay, this one, and this is your flux or the advection, okay, how they are basically being transported through the surfaces, okay, and that should be equal to the forces, okay. There will be some forces acting on the body, okay, that is the Newton's second law, that this entire thing we will see it shortly. This represents basically the rate of change of momentum, and that will be equal to the forces, okay. So, what are the forces that we have in fluid? Okay, so, we are writing in term which is basically the due to the stress and plus due to the body force. Okay, so, I am using G, which is which is typically used in the simulation, which is the gravity force, okay, but it can be magnetic force or it can be any electric force or any force that you want, right. So, if you are let us say doing the magnetic dynamic solution, then it will have the magnetic force, right. Now, the most critical quantity here is the tau I j, right. If you want to write this expression in the vector form, so that will be del rho u by del t plus del dot rho u u, okay, and which will be equal to tau, okay, and plus rho g. The vector here also. Okay, so this is how you write in the vector form, and many of you may be familiar with the vector form. So, that is why I wrote it for you, but this does not, this is very trivial that you have rate of change is equal to the forces, rate of change is equal to forces, but then what are the forces that we have in the fluid particle, and that is where the derivation becomes very important, and this was basically given by Navier and Stokes separately. Okay, and that is why it is called the Navier-Stokes equations. So, before that also people tried to derive this expression, but they did not consider the viscous forces, right. So, that is why they are not the complete conservation law. You can have, you might have heard about the Euler equation, where you do not have the viscous term, and that cannot be applied to any fluid, any realistic flow where you have got the viscosity. Okay. Now, if you look at the variables that you have here, okay, as of now you have u, v, w, okay, but also rho if it is compressible, okay, but also you have this tau term. Okay. What is the tau? This is a stress term, the stress that the fluid is experiencing, right. So, we need to find out the stress. Okay. Now, the stress if you see in a fluid element, okay, if you have a 3-dimensional fluid element, okay, let us say this is your 3-dimensional fluid element, okay, this is your I, okay, this is your j, and let us say this is your k. Okay. So, in that fluid element you can have forces which is let us say this tau is basically tau I j, it has got two indices. Okay. So, tau I is basically in the direction I mean where the element is present, and j is the direction in which the force is acting, right. So, if you take let us say section here at a given I, okay, and then you apply the force in the same direction, right, then you will get this. So, if I equal to 1, so then what you will get is here is basically tau 1 1, right. But in the same element you can apply the force in the upward direction, okay, and if that direction is j or y, that will be tau 1 2, right. So, it is I equal to x, j is equal to y, and k equal to z, right. And similarly you can apply in the z direction, that will be tau 1 3, right. Similarly, if you cut across let us say in the vertical direction, okay, and then you can have basically tau 2 1, tau 2 2 and tau 2 3. Similarly, if you cut in the span wise or in the third direction, which is the k direction, z direction, then you will have tau 3 1, tau 3 2 and tau 3 3. So, the tau is now a matrix, okay, it is actually a tensor, matrix is not the correct term, it is a tensor, okay, tau 1 1, tau 1 2, tau 1 3. Although it looks like matrix, okay, but there are certain rules which are applicable to tensor, but not which are not applicable to the matrix. Okay. Tau 3 1, tau 3 2, tau 3 3. This is tau 2 1. Okay. Now, you can see that there are some in the diagonal, which is tau 2 1, tau 1 1, tau 2 2 and tau 3 3. Okay. So, these are basically the stress in which the acting force in the same direction in which the element is present, right. So, these are basically the normal stresses. So, it is tau 1 1, tau 1 2, tau 1 3 are basically the normal stresses, okay, or the linear stresses, right. Whereas, this tau 1 2, tau 1 3 or any other quantities, basically what they have this tau 1 2. So, this is the direction is 1, but the force is acting in the j direction or the second direction. So, what it will do? It will give you some shear, right. So, that is basically the shear stress. So, these are basically the normal stresses and these are the shear stresses, right. All this tau 1 2, tau 2 1, tau 3 1, tau 2 2 3 and so on and so forth, right. And now, remember this tau is a symmetric tensor, that means your tau 1 2 will be equal to tau 2 1. Similarly, tau 3 1 equal to tau 1 3 and similarly tau 2 3 equal to tau 3 2. Okay. So, this is a symmetric tensor, but even if it is a symmetric tensor, you have at least 6 unknown quantities, which is tau 1 1, tau 2 2, tau 3 3, tau 1 2, tau 2 3 and tau 3 1, right. So, how do you get these 6 stress quantities, and then only you will be able to basically solve this Navier-Stokes equations, right. So, let us try deriving this stress quantity. Okay. Now, if the element, the fluid element is at rest, okay, then also some stress is acting on this, some force is acting on this. And what is that force? Is the pressure force, right. You can have pressure acting on from normal direction everywhere. So, it will be part of the normal stress, right. So, the pressure is acting on this, right, if the fluid is in static state. So, this force is called the hydrostatic force or hydrostatic stress. Okay. Force per unit area is called the stress, right. But when the fluid is in motion, you will have additional stresses because of the motion of the fluid, okay, because you will have the velocity changing across layers, okay. So, that will give you the different kind of stresses, right. So, that will be called as the deviatoric stress, right. So, we will basically divide our tau ij into two parts, one is the hydrostatic stress, another is the deviatoric stress, okay. Now, I am introducing a term just to represent it properly in your using tensor form is introducing a Kronecker delta. Delta ij is Kronecker, I hope I am right, okay, Kronecker delta. Sometimes they do not use C, okay. So, what is the property of this Kronecker delta? So, delta ij is equal to 1 if j is equal to 1, okay, if j is equal to 1, otherwise it will be 0. If j is not equal to 1, then this will become 0. So, the delta ij value will be 0, sorry, j is equal to I. If j is equal to I, then it is 1, if j is not equal to I, then it is 0, right. So, if you use this relation, then you will see that delta ij, the pressure will only act when I equal to j. So, then if you have, you will, if you write this stress term tau ij, let us say for only for hydrostatic, okay, then it will be only minus p, because this will be delta 1 1, it will be 0, which is 1 2, this is 1 3 0 0 minus p 0 0 0 minus p, right. So, that as you can see that this is only acting the normal direction, because pressure always acts normal to the surface. So, you can get this hydrostatic term. So, now we have basically found one term which is the hydrostatic term, which acts even if the fluid is in static state. Okay. The more complicated part is the deviatoric part. Okay. Even in the deviatoric part, we have two terms which are basically the normal stress or the linear stress as well as the shear stress, and we will shortly derive those things. Okay. Now, what we know from our experience or what we have discussed in the very first class is that in the fluid the stress is proportional to the strain rate, right. So, if you are simple minded and the flow is just 1D, so you can write tau equal to mu du by dy, okay. That is what you might have studied in your undergrad, maybe the fluid mechanics course, right. But now, we have a strain rate tensor in our case, right, because if the flow is 3 dimensional, okay. So, if the flow is 3 dimensional, let us say this is your strain rate, okay. This value you know, remember, strain rate tensor I am writing, okay. So, you will be known from your equation. So, this thing you know, you do not know the tau, but we know that tau is related to somehow this strain rate tensor that we have, okay, del u by del x, del v by del y, whatever, okay. Now, this strain rate tensor can be written in two parts, okay. One is del u I by del x j plus del u j by del x I, okay, and plus half del u I by del x j minus del u j by del x I, right. Now, if you closely look both the parts, okay, I have not done anything, I have just basically added this del u by del x I and subtracted that, right. So, if you observe it closely, okay, this is basically your symmetric part, right. So, if you write your strain rate tensor here, okay. So, this is the symmetric part and this is the antisymmetric part, okay. Let me complete this thought first. Antisymmetric or sometimes also called exosymmetric, okay, tensor, and I am sure you know this quantity. What is this? This is basically the vorticity, right, and this is your symmetric tensor. What it does? It basically deforms the fluid, deforms the fluid element, right. So, this is what is important for your stress, okay. This will not cause you any stress in antisymmetric tensor because this is a vorticity and that will give you the rotation, right. So, the symmetric tensor is what is important for the derivation of stresses, okay. So, I will write it as E I j, okay, and this will be basically half omega I j, but remember this this is not contributing to stress, contributing to stress, okay. and this is antisymmetric, you can see it easily. So, if I can write it as a I j, or just if you write omega I j, right. So, that will be del u I by del x j minus del u j by del x I, right. So, if you do omega j I, that will become del u j by del x I minus del u I by del x j, right. So, that is basically minus omega I j, right. So, you can see this is an antisymmetric tensor. On the other hand, if you write this E I j, okay, you can exchange j and I, it will remain the same, that will become A j, E j I. So, this is the symmetric tensor, right. So, you can write the symmetric tensor here. Okay. So, the E I j can be written as basically del u by del x, here it will be half del u by del y plus del p by del x, because it is I equal to 1, j equal to 2, I equal to 1 and then j equal to 3. If you do, that will be half del u by del z plus del w by del x, and similarly you can write the entire standard tensor. So, this will be del v by del y, this will be del w by del z, this quantity will be similar to this, and you will have some more quantity here. Okay, this will be similar to this. Okay, and then you have quantity which is this is I equal to 2 and j equal to 3, right. So, that will be half del p by del z plus del w by del y, and here it will be half del w by del y, okay, and del v by del z, okay, and this would be half, this is I equal to 3 and j equal to 1, right. So, this will be half del w by del x plus del u by del z. Okay, please verify this, that what we are doing is correct. Okay, this will be probably half del u by del y plus del u by del x. Let us see how many independent quantities that we have, 1, 2, 3, because a symmetric tensor. So, this is 4 and this is 5 and this is 6, right. So, you have 6 standard tensors, okay, that is present. Okay. So, we our goal is to basically use this standard tensor and derive the expression for the stress term. Okay. Now, I am going through this derivation because it is important to understand why the pressure in the incompressible flow is not a thermodynamic pressure, right. So, you might have read about this that in the case of incompressible flow, you do not use the equation of state, okay, and that is why you have to go through this pressure Poisson equation, right. In the compressible flow, we use the equation of state, and that is very helpful, because you can relate the pressure to the density and the temperature. Okay. So, let us try to find out that why we cannot use the thermodynamic pressure in our incompressible flow. So, for that we have to basically go through the derivation, right. So, what we are going to do is basically we are going to basically express our stress in terms of strain, right. So, strain rate tensor is basically E k L and C I j k L. So, why I am writing like this, why E k L, because I g is are the free index, okay. It cannot be basically used here. So, what I have done here, this is a tensor of order 2, right. That is the order 1 tensor is basically a vector, right, and this is also a tensor of order 2, right. So, in order to basically use one tensor and get another tensor, what you need is a transformation tensor, and that has to be tensor of order 4. And why do you need tensor of order 4? I mean, to understand that, you can just you might have read about this transformation matrix, right. So, let us say if a vector, okay, which is B equal to A I plus B j plus C k, right, and you want to transform it to another vector W, right. So, if you want to do that, okay, so you would require a matrix, okay, to transform this A B C into another value for another basis vector, right. So, this is what is your transformation matrix. So, if you have let us say this is T11, T12, T13, T21, T22, T33, T31, T32, T33. So, then if you want to get this first element, let us call it capital A, that will be equal to T11A plus T12B plus T13C, right. So, this is your first order tensor, and in order to get another first order tensor from that, okay, you need a second order tensor, right. This is the tensor of order 2, right. Similarly, you have a second order tensor which is your stranded tensor, and we want to get this our stress tensor from that. Okay. So, we need a tensor of order 4, okay, that is which is what is Cij right. Now, it is a very complicated tensor because it will have how many elements. So, in vector you have is a first order tensor. So, your element will be 3, right. This is a second order tensor. So, that will be element what how many elements we had was. So, number of elements will be 3 square, right. So, 3 to the power order of the tensor. So, if you have fourth order tensor, that will be 3 to the power 4, that means we will have 81 elements, okay, in this tensor, and finding out all the 81 elements is not easy, okay, for a given fluid, right. So, we will try to reduce it using some property of the fluid, okay. So, that we can find out thisCijkl into something that we know. For example, we know the viscosity of the fluid, and we also know that our stress in a very simple flow depends on the viscosity, right. So, our goal is to findCijkl, okay, in terms of let us say viscosity or related quantity, but it should be a variable which does not have too many unknowns, right, like we have 81 unknowns here, right. So, what we will do, we will assume that the fluid is homogeneous and isotropic, okay. So, what do you mean homogeneous? Homogeneous means that is it is position independent. So, whatever quantity that we have, it is independent of the position, right. So, that is homogeneous. Similarly, what we are saying that is isotropic, that means it is direction independent. That means, if you rotate it, okay, across let us say any basis vector, the value will remain unchanged, right. So, if you assume these two quantities, you can write or represent thisCijkl into basically 3 variables, okay. Basically, okay, before we go there, we can write it in terms of so we are basically trying to find out a scalar from thisCijkl, okay, because we want to reduce this 81 unknowns, okay. So, this can be written, and the scalar S can be written asCijkl, and then it will multiply by you will require vector, because we need to basically contract and remove all these independent variables I, j, k and l, okay, b, j, c, k and d, l, right. So, these are the 4 vectors that we have, okay, which will each will contact withCijkl and ultimately give you this scalar, right. Now, if you assume that fluid is homogeneous and isotropic, right. So, that means it will be rotation independent, right. So, if you rotate it, it will not change. That means, if you can take 2 vectors at a time, you can let us say take A dot B, okay. So, this basically these are vectors. So, that is nothing but A B cos theta. Since that theta is not changing, right. So, what you can do, you can write this in terms of the series of 2 vectors, right. So, how many of such series that you can do? I mean, this say we are doing assuming the conditions of isotropy, right. So, that will become, so we can write in a series of 3 vectors. So, this will be alpha A I B I and this is C j D j. Okay. So, we took A B together and C D together. Similarly, you can do beta, okay, A I, now you can take C I, okay, and then B j and D j, right. And similarly, you can take the third combination, okay, that will be your gamma, that is now we have taken A I, D I and then basically B j and C j, Okay. So, now basically we reduce our 81 unknowns to basically 3 unknowns, and of course, we have to fix this vector quantity, that is A I B j, I mean whatever the vectors that we have. We will again make use of our Kronecker delta, right. So, this can be written as alpha A I. So, now it is B I want to write in terms of B j, right. So, that will be B I delta I j. That means, so I am writing B I is equal to B j delta I j, right. Why? Because when j equals to I, then only it will be valid. So, this can be written as B j delta I j. Similarly, you can see this is C j, now I want it into C k, right. So, you could actually, because this is a repeated index, so you can use this C k d k. So, C k and this will be d l delta k l, right. Similarly, if you use this beta, so that will be A and C. So, this is A I and you want C k, right, C k delta I k, right, and then you have B j and D L, right. So, that will be delta J L and plus gamma A I and you have D is L, right. So, D L delta I L and then you have B j and C k delta k L, right. So, you can now compare, this is basically C I j k L, right. So, you can compare these values and this will give you C I j k L A I B j C k d L. So, this A I B j C k d L will get cancelled out. So, your C I j k L will become alpha delta I j delta k L, right. And okay, no. So, this is how we expressed it, and now it has to be multiplied by your E k L, right. Look at this expression, this is your tau I j, right. So, let us, so then your entire thing will be C I j k L E k L will become alpha delta I j delta k L E k L plus beta delta I k delta I L E k L and plus gamma delta I L delta k L E k L. Okay. So, before I go to the next slide, you can just see this is delta k L E k L, right. So, this can be written as E k k. What is E k k? Is basically del u k by del x k, right, or in other words, if you this is del dot u or basically del u by del x plus del v by del y plus del w by del z, right. So, this has become your alpha delta I j E k k, right. And similarly, you can use the expression here. So, this is I k and j l. So, you can reduce, basically you can contract it. Okay. So, this will become beta delta. So, if you contract it, this is I k and that will give you delta j l, right, delta I k delta j l, and this will be E k l, right. And similarly, you have gamma delta I L delta k L and delta E k L, right. So, if you do the further contraction, you will have C I j k L into E k L will be alpha delta I j E k k, right, plus beta you can contract it here, both L and k will be contracted, okay, and what we will get is basically E I j plus gamma E j I, right. This is the expression that you got, okay. This is nothing but your tau I j, okay. Now, you can further use the property of the symmetry, because this tau I j equal to tau j I, right. So, if you use this property of symmetry, you can show that your beta is equal to gamma, right. You can write an expression here and you will find that this beta equal to gamma. So, you can write this expression tau I j is equal to alpha delta I j E k k. Please go back and show this, that beta is equal to gamma and plus beta into 2 E I j. Okay. Now, you can basically we know that our stress is proportional to the strain rate, right, in the case of fluid. In the solid we have discussed this is proportional, stress is proportional to the strain, right. So, if you use this identity, so this is your strain rate tensor E I j. So, then your beta becomes your viscosity, okay. And then alpha is also a viscosity, okay, which is called, which is denoted as lambda. So, this is called the first coefficient of viscosity, and this one is the second coefficient, and this is related to the bulk viscosity, and it will only act when your dilatation is not 0. So, basically when del dot u is not 0, which you can see here also, because this is related to only E k k. So, let us write it here, lambda delta I j E k k plus mu 2 mu E I j, right. This is your tau I j, right. So, we related our stress to the strain rate tensor, right. Now, we want to find out how the lambda is related to mu, right. So, what we will do now is that take this stress of this tensor, stress tensor. So, we will add this tau 1 1, tau 1 2, tau 2 2, tau 3 3 and basically divide by 3, right. So, this is tau, what is tau 1 1? Delta, this is E 1 1, right, which is basically del u by del x, right. See I equal to j, right, plus 2 mu E 1 1, right, which is again the this is del dot u. Just one second. Okay. So, the tau 1 1 if you do, so this delta will become I will become 1, j will become 1. So, this is lambda and then this will be present. So, E k k is nothing but del dot u, okay, and plus 2 mu E 1 1, which is basically just your del u by del x. Okay. Similarly, you can have tau 2 2, which is lambda del dot u. Okay, I am missing the vector signs, so please be careful. Okay, 2 mu del v by del y, okay, and tau 3 3 is equal to lambda del dot u plus 2 mu del w by del z. Okay, so remember we have missed one quantity here, which is basically your so this is only the deviatoric part. So, you can have, you must have the pressure part also. So, that will be minus P delta I j, right. So, it will be there everywhere, or what you can do, you can write it as just only this is tau I j deviatoric, will be this, okay, this is tau I j deviatoric, and you have hydrostatic part also. So, that will be, this will be minus P and minus P. If you add 3, all these 3 and divide by 3, okay, take an average of that. So, this will be tau 1 1 plus tau 1 2, tau 2 2 plus tau 3 3 by 3 will become minus P, okay, plus lambda plus 2 mu by 3 plus lambda delta del dot u plus 2 mu by 3, and that is also del dot u, because del u by del x plus del p by del y plus del w by del z, that is also del dot u, okay. And we define this as a mechanical pressure, okay, we call it P mech. So, minus P mech is equal to minus P plus lambda plus 2 mu by 3 del dot u, okay. Now, this is an interesting term. So, this is the mechanical pressure, and what this is the thermodynamic pressure. So, this for this P you can use P equal to rho r T, but for this is the mechanical pressure, you cannot use P equal to rho r T relation, because that is not the thermodynamic pressure, that is a thermodynamic pressure plus you have something which is coming due to the divergence due to the volumetric change in the fluid, right. Now, it so happens that in I mean this P mechanical depends on the basically your the degrees of freedom, right. So, if the degrees of freedom are let us say only 3, that means only the translational degrees of freedom there. So, energy can be very I mean transferred only in the energy mode are only the translational, then this P mechanical and P will be the same, right. But if you have the vibrational component also or rotational component also, that means the degrees of freedom are higher. In that case your P mechanical and P will not be same, and your volumetric strain will play a role, okay, in determining the P mechanical. Okay, so, that is one thing, but another thing is that let us say if you have a system which is changing very fast, you are changing the thermodynamic state of the system very fast, then the system has to adjust to get the equilibrium. But sometimes the response time of the system is not similar to the time which is at which you are changing the system. Right. In that cases also your P mechanical will not be equal to P. But those are situations which are very rare situations. Okay. For example, if you have a balloon which is basically changing the state very fast, you are expanding and contracting it very fast, okay, then your P mechanical will not be equal to the P. But in most cases, okay, in our normal situations, okay, first of all, if the translation motion is only important, translation mode of energy is the only important, and other thing is if the change in the system is not very fast, then your P mechanical may be equal to P, and in that case you can write this lambda plus 2 mu by 3 del dot u is equal to 0, right. Now, here two things here, either del dot u equal to 0 or you have lambda plus 2 mu by 3 equal to 0. So, this is anyway valid for your incompressible flow. So, for the incompressible flow it will anyway go to 0. Okay. In other cases you get this situation lambda plus 2 mu by 3 equal to 0, that gives you basically lambda equal to minus 2 mu by 3. So, we are relating your second coefficient of viscosity for the with the first coefficient of viscosity, and so this is called the Stokes hypothesis. And why it is hypothesis? Because you cannot prove it. Okay. It can be proven if it is the only mode of energy is your translational mode, but in other cases it is an hypothesis, but it works well for most of the situations. There are two reasons. One is that either the del dot u is very small, okay, and then also it will go to 0, thus this entire term will go to 0, lambda plus 2 mu by 3, okay, or your lambda plus 2 mu by 3 is very small. Okay. However, if you go to a very high speed flow, okay, let us say the hypersonic cases and all, in those cases this term becomes very important, and your Stokes hypothesis may not be valid, because there the vibrational mode of energy becomes very important. The molecules start to dissociate, you will have ion formation, and in those cases you cannot use this relation of lambda equal to minus 2 mu by 3, and you have to basically look for the variation of the bulk viscosity. Okay. So, that is mostly in the situation where you have the hypersonic flows, and that is why have to basically do special treatment of the bulk viscosity. Now, let us finish this thought I mean for the normal situation. So, this we have already derived lambda and mu. Okay. So, lambda plus 2 by 3 equal to 0. So, if you use all these terms, so I have used this tau I j is equal to okay, minus p delta I j and plus sigma I j. Okay. This is the deviatoric term, and this is your pressure term. So, if you use that expression, we had this tau I j by del x j, right. So, that will become, if you use this tau I j form, so this is minus del by del x j p delta I j. Remember this this will only work when I equal to j, and because our direction is in I here, right, this is I am doing for rho I. So, this will become minus del p by del x I, right. And similarly, you have this sigma I j which will come here, and sigma I j I have written in the this form. This is nothing but mu and E plus 2 E minus okay, this is 2 E mu and plus lambda delta I j E k k, right. This is E k k is delta U k by del x k, lambda is equal to minus 2 by 3 mu, and E I j is basically del u I by del x j, half del u by del x j plus del u j by del x I. So, this completes our derivation. So, that means we can calculate the stress term using the velocity gradient that we have present. So, now the number of variables have reduced. Okay. The only thing that you need to know is now the viscosity, right, which is this quantity. Okay. The viscosity may vary with the temperature as it happens in the case of compressible flow, and we will have some laws to basically how to calculate the viscosity with the temperature, variation with the temperature. For incompressible flow, the viscosity can be assumed to be constant, because the temperature fluctuation is not there, temperature variation is not there. And for the incompressible flow, you can take this quantity to be 0, 2 by 3 delta I j del u k del x k, because this quantity goes to 0. Okay. So, at the end let us derive for the incompressible flow. So, incompressible flow you have rho equal to constant, that is one quantity. Okay. And del u k by del x k is equal to del dot u equal to 0. Okay. So, if you work that out, so then you will have del sigma I j by del x j. So, this is our sigma I j, right. So, partial sigma I j by del x j will be del by del x j, okay, and del u I by del x j plus del u j by del x I. Okay. And if you work that out, okay, and you will take the all three components. Okay. So, you will get this del u by del x square plus del to u I by del y square and plus del to u I by del x square del z square, right. So, which is nothing but del square u I. Okay. So, and recall that you need to basically make sure that del dot u goes to 0 when you are deriving this. Okay. So, those components will cancel out, and this is the expression that you get, and this becomes even simpler for the incompressible flow. There is no second coefficient of viscosity, and that is why all the terms is minus 2 by 3 delta I j E k k goes to 0. Okay. And it becomes very, very simple, it is a Laplacian term. Okay. And that is the reason, as we will study later, that in the case of incompressible flow it is more like a elliptic equation because of this presence of this Laplacian term, where in the case of compressible flow it is more like an hyperbolic system. Okay. So, with that we will conclude our thought. Okay. In the next class we will look at some of the non conservation form, and we will also derive the energy equation, and this was a quite extensive derivation. So, I would request you to please go back and basically work on this. Okay. And we will meet in the next class. Thank you very much.